So today I wanted to kind of introduce some of the work our group has been doing at mainly synchrotrons, but also a little on X-FELs and what I see as some exciting opportunities for high pressure studies at X-ray facilities. So I set up my talk to present a few examples of synchrotron and X-FEL studies from our group focused on looking at Earth and planetary materials. But first, a bit of introduction to high pressure. So why do we care about what happens with pressure? Well, it's a fundamental thermodynamic variable that can be used to induce profound changes in materials. If we look at carbon, at the conditions on our planet's surface, the stable form of carbon is graphite, which is a soft, opaque semimetal. Graphite then transforms into diamond with the application of high pressure and temperature, and the resulting properties could hardly be more different. Right now we have a super hard, transparent electrical insulator, a fantastic thermal conductor. So you have the same chemistry, but with a different structure, you have radically different properties. Pressure also greatly complicates and enriches the H2O phase diagram, producing many new crystalline phases and also a number of amorphous forms. If we look in the Earth's mantle, silicate rock-forming minerals undergo a dramatic coordination change from tetrahedrally coordinated silicons to octahedrally coordinated silicons with depth. And then if we take a look at the periodic table of elements at ambient pressure, the elements in yellow are found to be superconducting at low temperatures. If we add pressure, then the elements in purple also become superconducting, so nearly doubling the number of elemental superconductors. Okay, so then how do we reach high pressure? Well, the main tool our group uses is what's called the diamond anvil cell. So a diamond cell operates under a very straightforward principle. You apply force to the back of two gem quality diamond anvils that are compressing onto a sample contained in a gasket. And since pressure is force per unit area, we can generate very high pressures on a very small sample squeezed between the tips of these two diamonds with only a modest application of force. So you can access a very large range of pressures reaching hundreds of GPa. So this is millions of bars, and simultaneously vary temperatures by using a cryostat to reach low temperatures and laser and resistive heating techniques to reach high temperatures. There are different diamond cell designs for different kinds of measurements. And all of these cells are very portable. So basically they're pocket sized. So you can make measurements in your laboratory and then take the same cell to a synchrotron X-ray facility to look at the same sample under the same high pressure conditions at different beam lines. Or you can also pretty conveniently ship the cell, as we've been doing for the past year and a half during the pandemic, when we had to run experiments remotely. The diamonds themselves are quite small, so they're a fifth to a quarter of a carat. So the sample sizes are also very small. And so diamond cells are really more for reconnaissance studies, so to be able to explore a wide range of pressure, temperature conditions, rather than for bulk sample synthesis. But another advantage of diamond is that besides being the hardest material known to man, diamond is also transparent to a wide range of electromagnetic radiation. So they make very good windows to see what's going on in the sample at extreme conditions. So this is really important if we consider the requirements for high pressure probes. The first is that, of course, the probe must be able to penetrate the pressure vessel and reach the sample. And so you can use optical probes, but they can also be limited depending on the quality of your window and the sample. And then also you can hit the diffraction limit. Vacuum probes like soft X-rays, electrons, and ions are of course excluded. And then X-rays, you need to have hard X-rays. So in the axial direction, if you're going through the diamonds, generally you need X-rays that are above 10 keV. And if you go through X-ray transparent gasket like beryllium, you still need hard X-rays around 5 keV to reach the sample. And then also, as I mentioned before, the sample volume is quite small. So you need to have a probe where you can get a sufficient signal out of the sample. And so with the very small samples, neutron probes can be limited. So really this all points to the advantages of synchrotron X-ray techniques, coupling well to high pressure probes, where you have very small, bright, high energy X-ray beams. And also there have been a number of probes that have already been developed that are compatible with diamond anvil cells. So you have a suite of techniques for looking at characterizing samples at high pressure. Okay, so now I want to move on to some examples, give you a flavor of the type of high pressure earth science studies our group has been working on using synchrotron X-ray facilities. And so this first topic will kind of present an example where we use a suite of multiple synchrotron X-ray techniques to look at one problem. And so let's take the case of what happens when you mix iron and water at high pressures and temperatures. So at low pressure on the Earth's surface, iron and water react to form hydrated iron oxides and iron oxyhydroxides like goethite, FeOH. But what about at higher pressure temperature conditions in the Earth's mantle? So a former postdoc in our group, Jean Liu, looked at the iron plus water reaction down to the Earth's core mantle boundary conditions. And he found at more moderate pressures, so those below 80 GPa, and in agreement with previous literature, iron reacts with water to produce wustite, so FeO, and iron hydride, FeH. But at pressures greater than 80 GPa, an unexpected reaction between iron and water occurs. And so he found a new hydrogen-bearing iron peroxide phase, so FeO2H, formed alongside with FeH. And so we found the reaction products in this X-ray diffraction pattern on the right. So this new hydrogen-bearing iron peroxide has the same crystal structure as pyrite, so FeS2. And if you think about the periodic table, this makes sense that oxygen sits right above sulfur. So basically it's the same structure as pyrite, but with oxygen replacing sulfur in the cubic lattice. You can also have variable amounts of hydrogen where the hydrogen atoms sit in between these oxygen dimers, between different iron-oxygen octahedra. And one particular thing to note is that this phase is very oxygen-rich. It has an oxygen to iron ratio of 2:1. And you can also synthesize a hydrogen-free version of FeO2 from other iron oxides. So like hematite plus oxygen, you'll get FeO2 at high pressures and temperatures. This is also a really good material to study with a battery of synchrotron X-ray tools. So show diffraction, but we can also look at the oxidation state of iron and oxygen in this compound. So Jean collected iron K-edge X-ray absorption spectra for both the hydrogen-bearing and hydrogen-free versions, shown here, for different pressures, and also for a number of iron standards for comparison. So here's a plot of the first derivative of the absorption edge. And so the peak for this iron peroxide lines up really well with Fe2+ compared to more reduced Fe0 and more oxidized Fe3+ or Fe4+. So if the oxidation state of iron is close to +2, then for charge balance, this would suggest that the oxygen is actually more oxidized, so closer to -1 rather than -2. So we also conducted an X-ray Raman spectroscopy study to look at the oxygen edge. Now this is a very challenging measurement since we cannot access the oxygen K edge directly. So at 540 electron volts, this would be a soft X-ray measurement and we require vacuum. So we had to do then this X-ray Raman measurement, which is an inelastic measurement where we shift the incident and the scattered X-rays into the hard X-ray regime. And then the difference in the incident and the inelastically scattered X-ray energy is the oxygen edge. So here we can see that the oxygen edge for FeO2 has a significant pi star peak, which would be consistent with increased oxygen-oxygen interactions and the oxygen being more oxidized. So this, and again, to emphasize how challenging this measurement is, this one measurement took at 110 GPa, took 40 hours to collect at 16 IDD, so beamline at the advanced photon source. And then also in conjunction, we had collaborators conduct theoretical calculations, which showed consistent results. So basically that iron is close to +2 and that the oxygen is more oxidized than it would be in normal oxides. So it's closer to -1. Okay. We can also look at the electronic spin state and the magnetic behavior of this compound. So the electronic spin state of the iron 3D electrons can be probed by studying the iron K-beta fluorescence via X-ray emission spectroscopy. So then the intensity of this satellite peak, so this K-beta prime peak, then gives you information about the total spin momentum in the iron on the iron site. So we found that the K beta prime intensity decreases between 45 and 60 GPa, and then nearly disappears at around 60, 65 GPa. And this indicates that you're undergoing a spin transition from high spin to low high to spin to low spin. So you have electrons pairing around 65 GPa. And then we also collected a series of synchrotron Mossbauer spectroscopy spectra, which consistently show in the FeO2 with both hydrogen and hydrogen-free versions, a non-magnetic state, which is represented by these kind of clean single beat spectra. And then the spectra were analyzed using a CONUS program to extract the quadrupole splitting and the isomer shift for iron in the FeO2. And the values are found, values for both the the quadrupole splitting and the isomer shift were very consistent with FeS2 if extrapolated back to ambient pressure. Uh-oh. I'm so sorry. It looks like the PowerPoint decided to stop, so I get this wheel of death. I may have to close the program and restart it. Okay. Sorry about that. Restarting the program now. The next slide I'm going to show is just to say that, okay, so we've done this battery of measurements on FeO2. And then the question is, so, but is it even relevant to the Earth? So, right back to the print slide. It came up. Was there any evidence that there might even be this new phase in our planet? So from seismology, seismology provides us with our main observations of the Earth's deep structure. And so near the core mantle boundary, there were a number of interesting features that have been observed from seismology. And these include what are called ultra-low velocity zones and large low shear velocity provinces, which are characterized by both an increased density and a variable depression in shear and compressional wave velocities. And there have been a number of hypotheses that have been proposed for explaining these features. And so then our question was, well, what about iron peroxide? Well, we'd have to know the sound velocities and the density for this phase. So again, former postdoc Jean Leo, he determined the density and sound velocities for the our iron peroxide, both hydrogen and hydrogen-free, and using X-ray diffraction, and then coupled with another synchrotron technique, nuclear resonance inelastic X-ray scattering, you can get both compressional and shear wave velocities. And so what did he find? So compared to PREM, this is the preliminary reference Earth model. So this is basically a 1D model of velocity versus depth in the planet. And so it kind of gives you the average velocities. We find that our compressional wave velocity is 20% lower, shear wave velocity is 40% lower, and the density is 20 to 30% higher for the iron peroxide compared to the average values for the core mantle boundary. And so what that means is that if you mixed 50% of this iron peroxide with 50% average mantle, this would give you velocities consistent with seismic observations found in ultra-low velocity zones. And then if you mix 5 to 10% of the iron peroxide with, again, average mantle, this could match large low shear velocity provinces. So it doesn't prove that it's there, but it does have the right properties that you could match the seismic observables. So to quickly sum up this study, we found unexpected chemistry in the iron plus water system at deep mantle conditions. We used a battery of synchrotron X-ray probes to study this new material. And what's really interesting is we find that iron is well known to have multiple valence states, 2+ and 3+, and of course iron metal in the core in the Earth, but that oxygen can actually have multiple valence states, so -1, -2 in the mantle. And also these are possible candidates for explaining some of the interesting seismic anomalies at the base of the core, at the base of the mantle. And ultimately, we want to get at questions understanding volatiles in the Earth, like how what are the hydrogen and oxygen carriers in the deep mantle, and how are hydrogen and oxygen transported, stored, and cycled through the Earth. Okay, so now I want to move on and discuss an example where we use one technique that can be used to look at a number of deep Earth problems. So we used nanoscale transmission X-ray microscopy. So X-ray imaging is a widely used technique, and not just in earth science research, but certainly in earth science research. It's well known in petroleum and research engineering. So you can determine the distribution of, for example, porosity in this oil impregnated turbiditic carbonate sample. Also, you can differentiate multiple phases as long as you have sufficient X-ray absorption contrast. So here is an image of a diamond-bearing eclogite from Siberia. And the garnets are shown in this kind of orangey red color. The diamonds, you can even see that kind of cubic shape, octahedra shape, are shown in blue-violet, and then these bright yellow dots are sulfides. So these are some examples that are used in-house X-ray sources, and the spatial resolution is typically a few microns, but people have really been pushing the resolution, since in this case, you're not limited by the probe wavelength with X-rays, but rather by the quality of your optics. And so what can you do with the nanoscale transmission X-ray microscope? So you can do two-dimensional imaging in phase and absorption and contrast with very, very high spatial resolution. So here's an image of a Siemens star calibration pattern where these thin lines, the width is 30 nanometers. And then here I show an image of a zircon which we imaged in collaboration with Mark Harrison at UCLA. And you can see in these, inside of the zircon, these kind of hexagonal shapes. These are actually very rare carbonaceous inclusions, and they have the hexagonal graphite shape. And this is a Hadean zircon, so it's a super old mineral, almost 4.1 billion years old. And you can actually image this inclusion inside of this very, very old zircon. You can also conduct 3D tomography if you can collect enough 2D radiographs at different angles. And so here I just wanted to show this little movie, which kind of demonstrates an extreme case where you really shows the importance of having 3D information. So at different angles, no and yes can look the same, right? So you really need to have the whole three-dimensional information to capture what's going on in the sample. And so this little movie was made by Eugene Liu, and so I just really like it, so I'm showing it. The synchrotron also has the advantage of tunable instant energy, which can enable element and oxidation state specific imaging. And I'll show a little bit about that. Okay, so what we want to do is be able to use this technique to conduct 3D imaging at deep Earth conditions, so at high pressure and variable temperature. We can look at quench samples really well. So these are samples that have been synthesized at high pressure and temperature, and then recovered back to ambient conditions. Then we cut out a portion of interest and image that. We've also coupled diamond cells for in-situ high pressure imaging at room temperature. And so here we use a modified diamond cell for this purpose. For tomography, we really want to have as much side access as possible because we're directing our X-ray beam to the side of the axis, then rotating the diamond cell. So 180 degrees would be complete access. With this cross cell, we have about 160 to 165 degrees access. So we're still missing 50, 20 degrees of missing angle. And then since we're directing the beam perpendicular to the diamond axis, we do need to use an X-ray transparent beryllium gasket. Ultimately, we also want to do as simultaneous high pressure capabilities, and this is still on my list of to-do list. And so I'm going to show you some X-ray imaging that we conducted at the Stanford Synchrotron Radiation Light Source 6-2C, and then also at Sector 32 of APS. And I'll show you some examples then where we're looking at the problem of how do planetary cores form. So a number of mechanisms have been proposed for how you can separate an iron-rich core from a silicate mantle. And these include magma ocean, diapirism, percolation, deformation. It's not necessarily one of these mechanisms versus another. You could have multiple processes operating together at different pressures and temperatures. But if we really want to know more about these processes and get beyond these kind of schematic pictures, then we really need to know the information when you mix iron plus silicate or iron melt plus silicate at high pressures and temperatures. And so let's take a first look at some of these quench samples. So this is a sample of San Carlos olivine. So it's a silicate that's approximating the Earth's mantle, and then an iron sulfur alloy, so something that's approximating the Earth's core. And the sample synthesized at 6 GPa and 2073 Kelvin. So at this temperature, the iron sulfide melts. The sample is then brought back to ambient conditions, and a small chip of, so this dimension is about 10 microns, was imaged. And then these dark kind of transparent portions are the silicate matrix, and then these bright blobs are our iron sulfur alloy. Like this maybe. So you can see, first of all, because again, the chip is 10 microns, that we can definitely image submicron blobs. And there's even more structure within these blobs. So you can see more iron-rich regions and less bright sulfur-rich regions in the blobs. And then overall, the message here is that these very modest pressures, so 6 GPa, the melt will form, again, isolated melt blobs. And so the iron melt would, in this case, not be able to percolate efficiently between the silicate grain boundaries. And this is something that's already been known. Okay. But a graduate student of mine, Crystal, she wanted to study these iron-rich melt and silicate phases at much higher pressures and temperatures. So maybe percolation doesn't work at low pressures, but what about when we get into the lower mantle? So in this case, the starting mixture was, again, silicate plus an iron nickel sulfur alloy. She compressed the samples in diamond cells and then heated the sample to above the melting temperature of the iron alloy. And then we also collected diffraction at high pressures and temperatures at APS to confirm that the iron alloy was molten. So we saw a loss of the diffraction intensity and the rise of the amorphous peaks. Then we covered the sample back to ambient conditions, cut out a region of interest using focused ion beam, and then we imaged that section using nanoscale transmission X-ray microscope. And then as a further benchmark, we took a portion of that sample and then did some serial sectioning via focused ion beam SEM. Okay, so I'm going to show you results for 4 different pressures. And so here are the results for the 3D distribution of the iron alloy melt in a silicate matrix synthesized at 25, 39, 52, and 64 GPa. So I think the main thing to notice is that there's a dramatic change in the ion distribution from isolated pockets in these lower pressures to an interconnected iron melt network at the higher pressures. And so this demonstrates that iron may be able to form an interconnected melt network between the silicate grain boundaries, somewhere between 40 and 50 GPa. And then we see that the molten iron could efficiently wet the surface of the silicate grains. This would indicate a change in the percolative ability, so a huge increase in ability to percolate. Right. And then we compare these TXM results to a serial sectioning approach using the FIB SEM. So this is where you take an SEM image, fib off a layer, SEM image, fib off a layer, SEM image, fib off a layer, and then you can reconstruct all of these 2D SEM images into a 3D object. So in terms of resolution, they're similar, these two techniques. You do get a little bit higher resolution in the SEM in the 2D layer, but then you lose some resolution in the layer you're fibbing off. I think one big difference is the amount of time. So we can look at a much larger sample using X-rays and do the imaging much faster compared to the FIB SEM. And also the X-ray imaging is non-destructive, so we had to do the SEM second after we did the X-ray imaging because you're fibbing off all your layers. And then another potential advantage is that the TXM can be conducted in complex environments like high pressure. Okay. So do we get back to the results? We observed a change in 3-dimensional iron melt distribution from isolated pockets below 40 GPa to an interconnected network above 50 GPa. And this provides evidence that percolation could be an efficient core forming mechanism in the lower mantle early in Earth's history. This could have significant implications for the evolution of the planet, especially the Earth's early thermal history and the large-scale geochemical distribution of elements in our planet. All right. So then I just also want to say that there's also opportunities for 3D imaging beyond, of course, looking at these two phase mixtures. We can also look at the density of amorphous phases. So I want to show a few slides on this. So The external determination of properties of deep fluids and melts can be very challenging, especially the equation of state, so the pressure-volume relationship. And the main reason is because of the lack of a long-range order. So this means you can't determine the volume of an amorphous material using more conventional methods like diffraction at high pressure. But what about we can measure the volume directly through imaging? So for initial high pressure measurements, we want to demonstrate that we could determine the equation of state by direct visualization. So one of our first studies was looking at crystalline tin. So we used a heavy metal tin, which would give us good absorption contrast. And also, since it's a crystal material, we could then also collect the X-ray diffraction to have a benchmark for our imaging results. So we started with a 10 micron size tin sample. So here's a 2D radiograph, and you can see the two diamond culettes that are coming and compressing onto our tin sample. And then here we have the 3D renderings from our tomographic reconstruction. And then on the right here, I just plotted in red. These are the results from X-ray diffraction for the low pressure beta tin structured phase, and then also for the high pressure body center tetragonal phase. And then the blue dots are from tomography results. And so the main thing just to note here is that the tomography is very consistent with the X-ray diffraction. So great, benchmarked that this works. We then subsequently looked at a GeO2 glass, which is a prototypical network-forming oxide glass, also an analog for SiO2 since germanium is right below silicon on the periodic table. And we used FIB to cut out a 40 by 40 by 40 micron cube and image this cube at 11.12 keV. This is close to germanium KH to try to improve our absorption contrast. And so this was work from Yulin, who's my first graduate student and now staff scientist at SLAC. We can see from the 3D reconstructions, so you see these 3D reconstructions up from low pressure up to almost 40 GPa. And then we can count all of the volume in these cubes and get a pressure versus volume relationship. So sorry, this should be volume over initial volume. So you just see the volumes decreasing with pressure. And so the one thing to notice here is that although the density data appears to display a continuous trend up to the highest pressure, there's actually a change in the compressibility around 10 to 13 GPa. And then this complements our other high pressure XFs data on GeO2 glass, where we observed a pressure-induced transition from 4-coordinated germania polyhedra to 6-coordinated polyhedra. So emboldened by this success, we decided to look at more Earth-relevant compositions like SiO2 glass and silicate glasses. So SiO2 is made up of elements with not a lot of electrons, so this can be very challenging to get good absorption contrast. So in some of our earlier experiments, we tried coating our SiO2 cubes with a thin layer of platinum. And so this cube initially was 15 by 15 by 15 microns. And you can see how the volume within the coating changes. So looking at kind of the negative contrast inside the platinum shell. So between 1.3 and 30 GPa, we actually saw a pretty significant decrease in volume. So it was about the 30 GPa sample was half the volume of the 1.3 GPa sample. We did get a little bit worried that the platinum coating might be affecting our results. So then we just said, well, let's just try directly imaging the SiO2 glass. And so we cut out these discs and also imaged the volume that way. And then we found actually the results are very consistent. And looks like there's a change in compressibility around 30 GPa. That's probably also related to a coordination change in the silica polyhedra. Okay, so then regarding imaging, I also wanted to finally say a few words about spectroscopic imaging capabilities and really using the ability of your synchrotron source to change the incident X-ray energy. So this diagram shows that you get a dramatic increase in absorption when you compare right below and right above these K edges of these transition metals. So if we look at samples of the silicate plus iron alloy again, then if you image below and above the iron K edge, you can then see these red iron alloy blobs kind of pop out. And so you can get elemental and oxidation state distribution information. And so we looked at speciation. In the study of a pressure-induced charge transfer transition in bismuth and nickel oxide. In low pressure phase, you have nickel 2+ and a mixture of bismuth 5+, bismuth 3+. But around 4 GPa, you induce a charge transfer transition where you get transfer electrons from nickel to bismuth, resulting in only nickel 3+ and only bismuth 3+. And then you can follow these changes by looking at the nickel K edge. And then so with spectroscopic imaging, you can follow changes in the nickel K edge and see how the sample is actually transforming from the lower pressure phase, which is shown in red, and the higher pressure phase, which is shown in green. So you can actually image a pressure-induced redox reaction in 3 dimensions. Okay, so now more briefly, I just wanted to discuss some opportunities for using X-ray free electron laser facilities for high pressure X-ray studies. So synchrotrons and X-FELs are highly complementary X-ray sources. They have different advantages and challenges also for high pressure studies. And there are a number of hard X-ray FELs currently operational worldwide. But if we take a look at some of the properties of X-FELs compared to storage ring sources, one of the most obvious ones to notice is the exceptional brightness, about 1 billion times brighter than synchrotron sources. Although I guess with ESRF's upgrade to EBS, this should be like 2 orders of magnitude higher. At LCLS, which was the first hard X-ray FEL to come online, and it's located at SLAC National Accelerated Laboratory, so very close to where I work at Stanford. You have things to know about the X-FEL is that large number of photons per bunch, and then also very short bunch duration. And then for running high pressure experiments, one of the LCLS end stations is the matter in extreme conditions MEC instrument, which is located at the very end of this far experiment hall. And the matter in extreme conditions instrument LCLS, it uses optical lasers. So it's not static compression anymore, optical lasers to generate extreme conditions via dynamic compression. And then you can couple this very short duration of the dynamic compression with the ultra-fast and ultra-bright X-FEL X-rays that characterize the sample as the shock wave is moving through the sample. And then so I've already discussed static compression, and so how we can go to very high pressures and variable temperatures in a diamond cell. But with dynamic compression, you can reach even higher pressures and temperatures, especially with these very high-powered lasers. But you are more limited in the available in-situ diagnostic probes. With X-FELs, though, this is increased opportunities to doing simultaneous X-ray and dynamic compression studies. And so one of the first LCLS experiments from our group was led by Ariana Gleason, who was a postdoc at the time, but now is a staff scientist at SLAC. And she wanted to look at phase transition dynamics in SiO2. So again, SiO2 is a very fundamental material, also abundant on the Earth's surface. And it's been studied extensively both by static and dynamic compression techniques. And so we used MEC instrument to look at shock compressed SiO2 transitions, investigate how the structure evolves during dynamic compression. And so this would have implications for understanding transition pathways between SiO2 phases, and also could provide some constraints for what's observed at meteorite impact sites. And then here's a schematic for the experiment where we looked at a variety of SiO2 starting materials. This cartridge. Optical lasers generate shock in the sample, and then you use your X-FEL X-ray pulses at varying delay times to take time-resolved snapshots of the sample as the shock wave travels through it. And so here are just some X-ray diffraction data where we started with a fused silica starting material. So it's a glass, there's no sharp diffraction lines. You're not supposed to see anything in these panels because this is before the shock wave has been launched into the sample. But then 11.6 nanoseconds later, on the sample that was compressed up to 34 GPa, you can now see these diffraction lines or diffraction rings, and this is crystallized as stishovite, so octahedrally coordinated SiO2 phase. Also, the rings are quite smooth, so no evidence for preferred orientation or texture. And then you can integrate patterns for different delay times for different laser powers. So these are these little envelopes are for different peak pressures, and get information about different pressure and different time series. And we can see that the crystallinity develops at later delay times, and also it can fit the widths of the peaks to estimate grain growth. And we found that the stishovite grains nucleate and grow quite rapidly. What's going on today? I want to Go forward. Please don't die again. How many minutes do we have left? Yeah, ask that question.
We're coming up towards the end,
Okay,
Wendy.
I'm almost finished. That actually works
Okay.
as long as I can.
Okay.
I can move ahead. Oh no. I'm sorry, I'm going to restart it again. So I was going to show that you can actually map out the shock-induced metastability, because we can actually look at even much larger delay times. Okay, let me what's up. I don't know. Of course, this never happened when I was checking the presentation. Or let's get to the end. Okay, so let me move forward a little more. So then I just want to provide very briefly one other, so we don't have to just do diffraction. Actually, other X-ray techniques have also been rapidly being developed to couple with dynamic compression. So we can also do X-ray emission spectroscopy coupled with X-ray diffraction simultaneously on the same sample. And so one of the benefits here is that we can, with dynamic compression, you get very high pressures and temperatures and actually melt the sample. So you can look at the spin state of iron in a melt, dense melt. So this is actually the first time that that's been that's happened, and so this study hopefully will get submitted and published soon. And this has relevance for understanding, again, early Earth processes when the whole planet might have been molten, and also looking at exoplanets and super Earths. Okay, and then just to say that with the upgrades to these facilities, there's more opportunities to have even more brightness, and we can also, this would also enable some very photon star measurements like inelastic scattering. So we also think about going back and coupling a diamond cell with the X-FEL beam, because now even the average brightness would be quite high. So just to finish up then, pressure is a powerful dimension for exploration in many fields. This includes not just earth and planetary sciences, but also condensed matter physics and solid state chemistry, material science, et cetera, and pressure is a really powerful tool for expanding the field in which we can look for new novel phases and new phenomena. And then the X-rays are a very powerful probe for characterizing what's happening at high pressure. And I think what's really exciting is that we've only really scratched the surface of this very broad, wide area of research and the many opportunities for high pressure studies. So I wanted to acknowledge a research group at Stanford, both past and present, who made this work possible, collaborators from many institutions, and of course, funding agencies. And then thank you for your patience with my presentation and for listening. And if you have questions, you can of course ask them now, but also please feel free to email me. And so it can also converse that way. Great, thank you.